Hi, hello everyone. Now we are studying this graph theory from last few lectures. In last lecture, what we have seen is we have seen when we call two graphs isomorphic to each other, and we have seen what does it mean by connectedness of a graph, and given two graphs how to find the union of these graphs. In today's class, we will study what does it mean by n connectedness of a graph. When do you say a graph is weakly connected or strongly connected? And we will see, does there exist a path in a graph which touches upon each vertex, and does there exist a path which is going through all edges and coming back to where it has started. These are called Hamiltonian paths, Hamiltonian circuits, Euler paths, Euler circuits. All these things we are going to study in this class. In last class we have seen, if we have got a graph, like this, say for example, this is one vertex, this is one vertex, this is all one vertex. Sorry. If this is the graph that we have got, we will take this example. Here is this particular example, and we say this part, this graph is connected if if there is a path between any given pair of vertices, we call this a connected graph, otherwise not. This is what we call connectivity of a graph. And now let us find out in these three examples which is a connected graph and which is not a connected graph. By looking at it, we can always say that the first example is definitely not a connected graph, because this particular subgraph of this graph, that is this, and this guy is not connected. There is no path from 3 to 4. There is no path from 3 to 4, hence this guy is definitely a disconnected graph. How about this guy? Is this graph a connected or not? It looks like they are connected, but actually it is not. If you see this guy, in fact you nicely represent them. This will take this particular shape actually. So only when we draw it, it looks like they are connected, but in reality they are not connected. This guy and this guy, there is no path, hence this is a disconnected graph. This guy is very much connected, because you can find a path between any of its vertices, hence this guy is connected graph. Now, I mean, this is just a fun example. You can consider set of all 3-letter English words which has got some meaning, say job, cat, mat, any 3-word meaningful words in English, and consider this set as the vertex set. These are all vertices of the graph that I am going to plot, and the edges will be, I will connect 2 words, 2 vertices. Each vertex is a 3-letter meaningful English word. I will connect 2 words if one word can be derived from other word by changing a single letter. For example, I have got Rob, an English word. This is going to be a vertex of my graph. The graph will be very huge, you can imagine that. Okay, between Rob and Job, I will have a edge because R can be replaced with J, and I am getting this word called J, Job. Hence, I will connect Rob and Job. If you ask me, Rob, ant is another English word. Am I going to connect with ant with Rob? No, because ant cannot be derived by replacing one character from Rob. Hence, there will be no edge between Rob and ant. Whereas from Rob and Job, you will have an edge, and from Job and Jab you will have another edge. Okay, if I ask this question, is fun connected to car in that particular graph? Now you have got a graph and you know where to put an edge, where not to put an edge. In the resultant graph, I am asking this question, is fun connected to car? Yes, there will be several paths. In fact, from fun to car, from fun to fan, there is an edge, because by replacing U with A, you will get an fan, isn't it? From fan, you can go to far. By replacing N with R, you get another meaningful English word, that is far. From far, you can get car by replacing F with C. That is, this is one path. Another path can be like this: fun, fin, bin, ban, bar, car. This is another path. Now, in fact, if you are interested, you can write a little small program to find out, to actually represent this particular graph. You know how to represent a graph. You can represent a graph either with a adjacency matrix or adjacency list. You represent this particular graph. There will be lots of three-word English letter, three-letter English words. Represent all of them by vertices and connect them if they are if one can be derived from the other by replacing one character. If this is the graph, represent it and find out which three-letter words are not connected to each other. Find three-letter words which are not connected to each other, and in fact, I will define a component in some time now. In next slide, I am going to define what a component is, and taking that definition, find out how many components are going to be there in the graph that you have constructed. It's a nice experience. You will know how to represent the graph and how you manipulate the graph operations. So you can take this as a home assignment. And now, I'll define here what is a connected component and all. In this connected component, and finally you find out in the graph that you have you have programmed for, in that how many connected components are there. You can find it out. This is an exercise. Let us see what is a connected component. You know, given a graph like this, say if this is the graph that is given to you, this is the graph given to you. There will be several subgraphs of this guy. Say one simple subgraph can be this. This is one subgraph, and this is another subgraph. Say this is another subgraph. There are going to be several subgraphs. So given a graph, it may be connected, it might not be connected. For example, these are all the vertices, and these together is also a graph. There is no doubt about it. Of course, this graph is not connected. That is what you are going to say, because there is no path from this guy to this guy. Okay. in this given any graph, you find out maximal connected subgraph of G, that is called a component. What does it mean? A component should be a subgraph. Definitely for this graph, say for it to be a component, it has to be a subgraph, and then that subgraph has to be connected, and then it has to be maximal with respect to the property of it being connected. What does it mean? We will do with this example. Say we take this particular example. This is a connected graph or disconnected graph. Definitely this is a disconnected graph, and in fact if you write nicely, the graph looks like this. Then what I mean here by component is this a subgraph of the main graph that we considered? Definitely it is a subgraph of this, because the vertex set, that is 1, 5 is subset of the graph that we have got. What is the vertex set of the graph that we have got? 1, 2, 3, 4, 5, 6, 7, 8, and this 1, 5 is subset of that, and the edge set, that is 1, 5 is definitely a subset of the edge set of the original graph that we have got. Hence this is a subgraph. Is it connected or not? It is very much connected. In this subgraph, all the pairs of the vertices are connected. Here of course there is only one pair that is connected, hence it is a connected subgraph. The point is it maximal connected subgraph or not? Is it maximal with reference to the property of connected? That means there should not be existing any subgraph which is connected and containing this particular subgraph. Is that true in this case? What does maximal means is there should not be any connected subgraph which is containing this the subgraph 1, 5. No, that is not true. If you see the subgraph that is 1, 3, 5, this is a subgraph, this is a connected subgraph, and it is containing 1, 5, the subgraph 1, 5. Hence this guy alone, that means this guy alone is not a maximal connected subgraph. Let us see at least this 1, 5, 3 is a maximal connected subgraph or not. 1, 5, 3 is a connected subgraph. Is it maximal? Yes, it is maximal, because there is no other subgraph of this which is connected and containing this, isn't it? There is no subgraph which is containing this, and that subgraph should be connected as well. If you say, sir, I will take this as that subgraph which is containing our subgraph of 1, 5, 3, then I say, boss, this is a subgraph, but it is not connected, isn't it? There is no path from 1 to 6, though there is a subgraph which is containing that is not connected. Hence we say that this subgraph 1, 5, 3 is maximal connected subgraph. There is no subgraph which is connected and containing this particular subgraph 1, 5, 3. That is called maximalness, maximal property. Whereas if you consider only the subgraph 1, 5, this is not maximal connected subgraph, because 1, 5, 3 is containing the graph 1, 5, graph with subgraph with vertices 1, 5, and this particular graph, that is which is containing that, is connected. Hence this particular subgraph is not maximally connected, whereas if you consider the whole this thing 1, 5, 3, it is very much a maximal connected subgraph, and hence it qualifies to be a component. This is called a component. Now how many components are here? We will see it. This is one component, and this is another component, because this is also a maximal connected subgraph. There is no subgraph which is containing this and being connected at the same point of time. And this guy is a maximal connected subgraph, this guy is a maximal connected subgraph. How many maximal connected subgraphs are there in this? So 4. So in the last assignment, what I am trying to say is draw the graph of 3 meaningful English words with the property that edge will be there if and only if there is only if and only if one word can be derived from the other word by replacing a single character. This particular graph that you have got, see whether it is connected or not. If it is connected, it is definitely only one maximal connected subgraph, only one component will be there. If it is not connected, check out how many components are there. That is what the exercise is. Okay. Now we will introduce what does it mean by unconnectivity. It is very simple. You have got a graph and say it is a connected graph, and by removing how many number of nodes, this graph will become disconnected. The minimum number of nodes that need to be deleted from a connected graph to make it disconnected, and the minimum number of nodes is called unconnectivity. If two nodes have to be removed, minimum of 2 nodes have to be removed so that the graph becomes disconnected, I will say the graph is 2 connectivity. If 3 nodes have to be removed, so that minimum 3 nodes have to be removed so that the graph becomes disconnected, I say the graph is 3 connectivity, is having 3 connectivity. This is what is unconnectivity is. I say a graph is unconnectivity if minimum of n number of nodes have to be removed for it to become disconnected graph. And this is very much this is very much applicable in computer network. Say you have got a computer network, means that all the computers inside the network are connected, be it LAN, WAN or whatever it is. And their interesting thing is, by shutting down how many computers should go down so that network becomes disconnected. Obviously what we want is for a network to be stable, we would like more number of guys should be down for it to be disconnected. If only one guy is going down and whole network is coming down, that's not a good design. So with respect to that property, let us see among all these 4, let us rate in following graphs in terms of their design value for computer networks. So that means what is the best among all these things? I can straight away say that this one is anyway disconnected. This is the worst network among all because there is no connection at all. And look at this guy, and look at this particular graph. Look at this particular graph. This is definitely connected, but if this guy goes down, that means if this computer goes down, or if I remove this particular vertex, then the whole graph becomes disconnected. And even if this guy goes down, that means there is no connection between this guy, this vertex and this vertex, hence your graph becomes disconnected. If this guy goes down, your graph becomes disconnected. If this guy goes down, your graph becomes disconnected. So this is not a good choice, because going one is making your network down. If you look at this particular network, if you see this particular network, or for us it is just a graph, only one particular node, only if it goes down, network is becoming disconnected or graph is becoming disconnected, because even if this guy goes down, I can reach to all other guys from this via this path, isn't it? Even if this guy goes down, I can reach to this guy like this, I can reach to this guy like this, I can reach to this guy like this, there is no problem. And if this guy goes down, I can reach to this guy like this, isn't it, from anywhere to anywhere. The only problem is, if this guy goes down, then I have got a bigger problem. I can't reach from here to here. So this is second best here. You got 4 guys, can any guy going down make you disconnected. Here there is only one such vertex which makes your network down, and that particular, if your graph is in such a way that one vertex you remove, it is getting disconnected, we call that particular vertex a cut vertex. Means if you remove that vertex, your graph has been cut and you get 2 components. And you see this particular graph, this is the best, because any computer coming down or equivalently saying, if you remove any vertex from here, the graph will not become disconnected. If this guy goes down, still you can, from here you can reach all other guys, there is another path. If this guy goes down, I can go from here to here to here, here to here, here to here, here to here, and here to here, here to here. I mean, there are a lot of paths. If this guy goes down, I can go from here to here, here to here, here to reach all. If this guy goes down, I can go from here to here, here to here, here to here, and I can reach all the guys. So one guy going down or one vertex being removed is not making this network down or this graph disconnected. At least 2 guys need to be removed from this graph for it to become disconnected. Hence it is called, this graph is 2 connectivity, this is 1 connectivity, this is 1 connectivity, and this is anyway disconnected. Isn't it? For network to be nice, you would like n to be as big as possible, so that even one computer goes down, you don't care, your network is working as you want it. Only that computer has got a problem, let it go, no problem, other guys are not impacted. That is how you want it to be, because in this particular graph you want 2 vertices to be removed for it to become disconnected. Hence we call this particular graph is 2 connected. So formally defining, we say a connected simple graph with 3 or more vertices, we say it is 2 connected. If it remains connected when one particular vertex is being removed, okay, at least 2 guys are required to be removed, that is what it means. Obviously, I mean just extending the definition, n connectivity means n vertices to be removed for the graph to become disconnected. And one small observation, that whatever if you got 2 graphs, say G1 and G2 are isomorphic, if you got a circuit in G1 then you will be able to find the corresponding circuit in G2. Basically what I mean here is the circuit or simple circuit or a path for that matter are graph invariants with respect to isomorphism. What does it mean is you take a simple you take a circuit there, you take a circuit in G1, you will be able to get a corresponding circuit in G2. Maybe the names are different, but the circuit structure of the circuit remains the same. That is what it means by these properties, like simple circuit are invariant with respect to isomorphism. And you know how to make an adjacency matrix. We have seen it yesterday. We will make an adjacency matrix like this. You put all vertices as rows, and as columns also, V2, Vn, and if there is a edge, say Vi Vj, if there is an edge called Vi Vj, then I am going to put 1 in the here where this is Vi and this is Vj, otherwise I am going to put 0. If there is an edge called V1 V2, I am going to put 1 here. If there is no edge from Vn to V1, I am going to put 0 over here. That is how adjacency matrix will be formulated. So here you can actually, once you find A, you can find A square, A power k, you can find product. A square is nothing but product of A with A cube is nothing but product of A square with A. Similarly you can find out A power k, then in that product AK, say in the product AK, what you find out is what is the guy who is present in ith row and jth column. Okay, that particular integer, definitely it is going to be an integer because you have been always multiplying with integers. All the guys in A are integers, so A power k is definitely going to be an integer matrix. In that matrix, the ith row jth column value is nothing but the number of paths of length k from Vi to Vj. It represents from Vi to Vj how many paths are available. Definitely there will be a number of paths, isn't it? The number of paths with k length. You know what length of the path, how many guys are in between Vi and Vj, more or less. How many number of guys between Vi and Vj, that is the path or length of the path from Vi to Vj. How many paths of length k are available in the graph is being found out by finding the ijth element of A power k. I mean the math behind it is we are not seeing here, but we can easily prove this as well. Okay, this is an interesting result. Now let us see the very important portion of this graph theory, that is given a graph, can I have a circuit or a cycle which can start from a vertex and the path should actually cover all vertices or all edges and should back to the same vertex? If this particular thing might be happening, might not be happening. If it is happening, we will call it a Euler circuit. For example, if this is the graph as simple as this, we will say it as a graph will have a Euler circuit if I have a path that starts from this particular say vertex u. It has to traverse through all edges that are there in the graph and should come back to this vertex u. If I can have such a path, then I say this graph is having a Euler circuit. This is called Euler circuit. And similarly we can define path. I have got two vertices u and v, and if I have got a path from u to v such that all edges of the graph are being traversed in my path of u to v, when this particular path is there, I say there is a Euler path. For example, here I can start from here, I can go here, I can go here, I can go here, I can go here, I can come back to u again. Say if this is V1, V2, V3, V4, and this is say edge U1, E1, E2, E3, E4, E5. What is the path I am speaking here is u. This is a starting vertex, and then I traverse through the edge E1, then I will go to vertex V1, then I traverse through the edge E2, I go to vertex V2, then I traverse through edge E3 and go to vertex V3, and then I traverse through edge E4 and go to vertex V4, and then I traverse through edge E5 and reach back to the source vertex, that is u. If I have got such a path, this path is having one special property, isn't it? All edges of this graph are there in this particular path. Hence, and this path is an interesting path because its source and destination vertices are the same, hence it is qualified to be called a circuit or a cycle. So now we have got a cycle in this graph which is having all edges inside it, hence it is called a Euler circuit. Similarly, Euler path is, except the source and destination are the same, it is the same definition holds good. Source and destination are distinct, but from source to destination the path contains all the edges of the graph. Now Hamiltonian circuit is, if you have got a graph like this, a simple graph like this, then it says it has got a circuit. If it has got a circuit which can start from a source vertex and traverse through some of the edges and reach back to the source vertex, but in the path all vertices of the graph should be covered exactly once. No vertex should be covered more than once, and all vertices should be covered at least once, should be covered exactly once. What does it mean? U, V1, V2, V3, these are the vertices. Then let us see whether this guy has got a Hamiltonian cycle or not. The path that I take is U, and U, E1, V1, E2, V2, E3, V3, E4, U. First of all, is this a circuit or not? Yes, it is very much a circuit. I am traversing like this. I am traversing like this, and finally I have reached where actually I have started. So this is very much a circuit, and for it to be Hamiltonian circuit, all the vertices should be covered exactly once. Let us see the vertex V1 is in this path or not. Yes, it is there. V1, is it there more than once? No, it is there exactly once. Say V2, it is exactly once in this path. V3, it is there exactly once in this path. Hence, this circuit is called a Hamiltonian circuit that traverses each vertex in G exactly once. Hamiltonian path is also the same thing, except you start from source vertex and you reach destination vertex, and in between you cover all the vertices exactly once. Okay. Euler and Hamiltonian, the only difference is Euler circuit will make sure that all edges are covered in its travel, in its path. Hamiltonian makes sure that all vertices are covered exactly once. Now there are a couple of theorems. They are only if part is there, not only if part is not there. That is what is making to find whether a circuit, whether a given graph has got a Hamiltonian circuit or not. This particular problem is becoming very difficult because is not solvable. Here, if G is connected and it is a simple graph, and we know that degree of each vertex in G is greater than or equal to n by 2, then we say G has Hamiltonian circuit. But it is not, other way is not true. That is making this Hamiltonian circuit problem very difficult one. It is not a sufficient condition. When I say that I don't have, if I am not able, if my graph is not satisfying this particular condition, I cannot say anything about Hamiltonian circuit of this graph. Okay, it is only one way true. If G is connected and it is simple, having n number of vertices, then and degree of each of the vertex is greater than or equal to n by 2, then G has a Hamiltonian circuit. This we can say, nothing more than that. If it doesn't have, we can't say anything. It can still be a Hamiltonian. And as a corollary to it, if degree of u comma degree of u plus degree of v is greater than or equal to n for every pair, then also we can say that it has got a Hamiltonian circuit, and we can't say anything about the converse. So this Hamiltonian circuit is really a big problem. It is called an NP complete problem because there is no way that we can find whether a graph G has got Hamiltonian circuit or not in polynomial time. Polynomial time and all we will get to know when you study algorithms. See, as simple as this, you understand like this. Given a graph, I don't have an easy algorithm, an algorithm which can be solved nicely, that is existing, to find out whether there is a Hamiltonian cycle or not. I will not be able to do this to find it's to find a Hamiltonian cycle is there not, it is a very tough problem, and if n runs into say hundreds, you may not be able to probably find it out. It's a very complex problem, and in computer science what people have done is, there are some problems which are very complex, they are all called NP problems, NP hard problems and all, and among them they classified some problems, 20-30 problems, wherein if you solve any one problem in that particular class, then all other problems can be equivalently can be solved nicely, can be solved in polynomial time. And this Hamiltonian circuit problem is one among such 30-40 problems. That means if Hamiltonian circuit problem is solved in polynomial time, there are lots of other open problems which have been found difficult all these years can be solved in polynomial time. They are reducible. Most of the problems are reducible to this Hamiltonian circuit problem. For us to understand Hamiltonian circuit problem, it is very simple. Given a graph, can you say whether there exists a Hamiltonian circuit or not? As simple as this. It is called an NP complete problem. Basically, this problem has been there quite in 17th century, where you got a town like this, where this is land area and this is water. This is land area. This is the land. B, C, D, A are all lands, and this is the river is flowing like this, and you have got bridges like this. This is bridge. This is bridge. This is bridge. These are all the bridges. Then the problem asked is, you start from one place and you have to come back to the same place, covering each bridge exactly once. Can you do it or not? In this particular example, it's same simple thing. You start from one place and you have to reach the same place by going through each bridge exactly once. This is the problem pondered for quite some time, and finally Euler is the guy who could solve this problem, and in fact he said it in a negative way. And if you actually translate the whole problem into graph theory problem, it is something like this. You got A, B, C and D, and you have got bridges. From A to D there is a bridge, from D to C there is a bridge, from A to B, from say A to B you have got two bridges, so two edges. From C to B you have got two bridges, hence you got two edges. The point asked is very simple now. Does it have a Euler circuit? That is what is being asked. You start from one place, maybe you start from A. Can you go back to, can you traverse through each edge and come back to A or not? This is what is being asked. And the theorem that we are going to see in some time, it is not, you cannot do this particular exercise. That means you cannot start from one vertex here and traverse through all the edges and come back to the same vertex. Is not going to happen. Simply because the theorem there says is that for a graph like this to be having Euler circuit, each vertex should be of even degree. Then only you can have a Euler circuit in it. Otherwise you are not going to have Euler circuit in it. If you see this particular graph, this edge, this vertex called D is having 3 as its degree, isn't it? Hence this this particular graph cannot afford to have a Euler circuit. The corresponding theorem is this. This theorem says a connected multigraph has an Euler circuit if and only if each vertex is having even degree. It means this, in this particular case, whether this graph is Euler or not, if each vertex is having even degree, then we can say it. Or otherwise, if somebody comes and says that, sir, I have got a graph which is having, say, Euler circuit, then I can always conclude that that particular graph is having vertices of even degree. That is what I can conclude. That is what this theorem is telling us. And we will see one portion of it, that is, suppose the given graph has Euler circuit, then we can prove each vertex has even degree. Suppose you have got a graph G, and what does it mean by saying it has got a Euler circuit? It means that there is a path like this, isn't it? There is a vertex called U. There is a vertex U from where you are starting your journey and finally reaching back to the vertex U, and you, on the way, you are traversing through each of the vertices. Okay, we will write down the path from U. Say you are going to a vertex E1, through a G1 you go to vertex V1, E2, V2, E3, V3, so on, En, Vn, probably this is same as U. So you are traversing through all edges in the graph, exactly all the edges in the graph. All the edges in the graph are being covered over here. Okay, now if you carefully observe, we will count the degree of each vertices over here. What is the degree that is contributed to U when I say there is an edge from U to V1? 1 is being contributed to the degree of U, isn't it? And when again there is an edge, there is say Vn minus 1, from Vn minus 1 to Vn there is an edge, what, and Vn is nothing but U anyway, because this is a Euler path, that is what is given to us. Vn, there is an edge from Vn minus 1 to Vn, that is En is given to us, that is there is an edge from Vn minus 1 to U is given to us. One more degree, there is an edge from to U, so one degree is added to 1, so at least degree of U is going to be 2, because one edge is going away from U and one edge is coming on to U, so the degree will be at least 2. And take now any vertex over here, say vertex V2. What is the degree that is being contributed to V2 in this path? There is an edge that is coming to V2 and it is going away from V2. The edge that is coming to V2 is E2 and going away from V2 is E3. I mean, there is an edge coming and going. So 2 is being contributed to the degree of the vertex V2. And you take, for that matter, any vertex, a degree of 2 is being contributed to its degree. And of course there is no issue, one vertex is being repeated in this path, absolutely that is okay. V2 can be repeated over here somewhere, but if it is repeated also, it is contributing 2 to its degree. So wherever how many times it is appearing in this path, so many 2's will be contributed to its degree. So the degree of any vertex will be even, because whenever it is appearing in the path, it is contributing 2 to its degree. Hence all vertices will be having even degree. Of course, anyway, u and u is having even degree, and all the guys in between are also having even degree, because whenever it is appearing in path, it is contributing 2 to its degree. Hence we can prove the part of if a connected multigraph has a Euler circuit, then we can prove this way that each vertex, we can prove this way, the way that we have just studied, by taking a Euler circuit and all, by approaching this way, we can prove that each vertex has even degree. Say with a similar approach like this, we can prove even the converse part of this. And finally, what we have done in this particular class is, we have seen what is unconnectedness of a graph, and we have seen what is Hamiltonian circuit, Euler circuit, Hamiltonian path and Euler path. Okay, and we have seen both necessary and sufficient condition for a graph to have Hamiltonian, for a graph to have Euler circuit. Okay, let us see in the next class the trees. How do we define a tree and what some of the properties of trees? Okay, thank you. Bye.